Hello everyone, welcome back to the fourth lecture of the last week, that is week 12. We are continuing with the curve tracing. So, here we will have some examples and we will explore much more the curve tracing properties. There were 14 properties for the curve tracing and we will go to check each one individually. So, let us start with one of the example of very famous example. We call it sometimes straight function and greatest integer function, so on. So, sketch the graph of the function y equal to greatest integer x, right? That is given. So, I will check a required number of properties and then on the basis of those properties, I will sketch this problem in by the hand itself, right? So, for doing this, first of all, we have to simplify it. There is no need to simplify because the function is itself in a simple form. So, that is why there is no need of simplifications. So, the second one was to use the domain and range. So, as greatest integer of x is defined for each real number on the real line. Therefore, the domain is itself the whole real number r, right? And the range is set of all the integers. Since its name is already a greatest integer, that means it is only containing integers itself, right? So, we had the domain as a whole real number and range is only integers, right, z. The curve lies in the first and the third quadrant because either x is greater than equal to 0 or y is greater than 0, right. X is less than equal to 0 and y is less than equal to 0. So, that is our simple specification based on the properties of the function by investigating its domain and range. Symmetry. Now, for the symmetry, if I put x by minus x, then it is symmetrical about the y axis. So, let us put here, we get the different value, therefore, greatest integer is not symmetrical about y axis. Also, y equal to integral x is not odd function, thus not symmetrical about the origin. So, point of intersection with the axis, if I put x equal to 0, we will get y equal to 0. So, origin is one of the intersection point. Thus, the curve passes through the origin. Also, when y equal to 0, x lies between 0 to 1, right. The graph lies on x axis, right. So, third property that we have done. The fourth property, points of discontinuity. So, y equal to greatest integer is discontinuous at every integer point, hence there is a break in the graph at every integer point. So, remember this one, this function y is discontinuous at z. In every interval n to n plus 1, its value is constant and is equal to n, right. We had done this. Relative maxima. Since y equal to greatest integer function has no maxima or no minima because it is defined for all real numbers and it has a specific integer value, therefore, there is no maxima or minima for this function. Now, can we check for asymptotes? Yes, there is no asymptotes as you cannot have a denominator or numerator. So, you cannot make the denominator tends to 0 or either numerator tends to infinity and so on. Concavity, the graph is neither concave upward because it is a constant between the n and n plus 1, right. So, that is why it is not this one. Now, based on this one, let us start with the 0 and 1 first. So, if we have 0 and 1, y equal to greatest integer x, if I want to find out 0 to 1, right. So, what we are looking for? We are looking for here 0 to 1, these values, and what will be the greatest integer of this value? Obviously 0, right. So, here is this value, this is the value, and if it is lying between 1 to 2, right, here 2 is not included in that one. We are looking for n to n plus 1, where n we are going to take that one and n plus 1 we are left. So, how much the value? The constant value of this as 1, right? Similarly, so the whole y equal to, this will give you y equal to 0, this will give you y equal to 1, and if you have a 2, 2, 3, then y equal to how much? 2, right? So here you will see this is 2, and so on. Similarly, can we have for 0 to minus 1, 0 to minus 1. So x lying between 0 minus 1 to 0, we can say minus 1 to 0. What will be the value? The y is equal to minus 1, the greatest integer less than that number. So this is the greatest integer less than that number. There is all those here, right? Similarly, between these one, the integer is this. So graph is the stair type of things. First stair, then discontinuity, then first stair, then discontinuity, again the stair, then discontinuity, then horizontal, then discontinuity, and so on, right? So it's a stair type of the function, and each type you will see the lowest integer and will be its value. So we call it the greatest integer function, which are each one, as you can see here, at the z, whatever the z you will see, each z at each point of the z, it is discontinuous. So we had traced based on at least 7 property we had checked. We can check 14 property as well, but there is no need. We had a complete graph of y equal to greatest integer for 7 of this one, right? So 7, only specified 7 properties will give you the function values. Similarly, now we will look at for concave upward and concave downwards. So concave upward, look at the graph A, and as you can see here, this is the concave upward now. So an arc of a curve y equal to fx is called concave upward if at each point of its curve the arc lies above its tangent line, right? So you will how you have to check that? You have to check that whether the curve of each point, if you trace the tangent at that point, the whole curve is lie upward of that tangent line. And if it is in reverse, so something like this. So if you have this type of cone, and we can say that this is the upward one. And if you have the downward, this is called that concave downwards. So how you can use those mathematical words? So for mathematical, we are now going to trace its derivative, and then we will pull out how the derivative identified the concave upward and concave downward, right? In the previous lecture, we had seen that the concave upward, that means double derivative of that curve y with respect to the x is greater than equal to, strictly greater than 0. Similarly, for concave downward, we had seen that double derivative of y is less than 0. So these are the mathematical tools to use that one. Now for a figure, as you can see here, this is a tangent line, and each point of this curve above to the tangent line, right? So arc lies above that tangent line. If y equal to fx is concave upward curve, then x increases and f dash of x is either of the same sign and increasing, or changes sign from negative to positive in this one here. As you can see here, here it's a changes the sign. F dash of x, the first derivative, changes its sign from this to this, but it's a still a concave upward, right? In either case, f dash x is increasing, and so f double dash of x is greater than 0. So what we have told that double derivative must be greater than 0. This will implies that the curve or arc is the concave upward, right? Similarly, concave downwards, thus the reverse it. That means we are looking for the tangent line of each point or any point of that arc, and if each point of those arcs below to the tangent line, then it will be a concave downward. And how to identify the things? There are two different scenarios we have. In the first scenario, you have a double derivative. So calculate the double derivative and find out that each point of the arc must be below to that tangent line. And the second one, if you see that the changes of the sign of the first derivative occurs, then this will be a concave downward. So see here, this has been changes their sign, and here each point lies below to the tangent lines. And how you can test by the second derivative? If the second derivative of the curve y is less than 0, then it will be a concave downwards, right? Now, point of inflection. A point of inflection is a point at which a curve is changing concave upward to concave downward, or vice versa, concave downward to concave upward. So as you can see here, this is the concave downward, right? And this is a concave upward. So it changes the sign, and that's why it is a point of inflection. So a curve fx has one of its point x equal to c as inflection point if the double derivative of the function at that point c is going to be 0, or at that point the double derivative is not defined, right? So the first condition is this, and the second condition, if double dash x changes sign as x increases through x equal to c. So I mean that point, the double derivative if changes their sign, then it is the inflection point. The later condition may be replaced by, so f triple dash of c is not equal to 0 when f triple dash of c exists. Thus x equal to c is a point of inflection if double derivative is equal to 0 and the triple derivative is not equal to 0 at that point, where we are calling the point of inflection. Now, what is the method to find the concavity? That means concave upward and concave downward and the point of inflection and so on. So in any interval, not the single point, but in any interval, how we can do that? So let y equal to fx be a given curve in a open interval AB. First of all, you have to find out the first derivative, then the second derivative, check their signs. If the first derivative changes their sign, or second derivative has the positive or negative in one interval, then that will give you concave upward or concave downward, depending on how the double derivative of y with respect to the x is greater than 0 or less than 0. If it is greater than 0, it will be a concave upward. It is less than 0, then it is a concave downward, right? So we have a 4 step here. We have to find first derivative, then second derivative, then greater than 0, check the sign of those, and then depending on these methodology, you will decide whether it is a concave upward or concave downward. So here is the first problem, that sketch the graph of a function y equal to x cube. So we have to find out firstly simplification. There is no need to find the simplification. So we are going for a domain and range. Y equal to x cube is a very simpler and a smooth function, and there is no critical point at all. So it is defined for whole domain. That means the domain is the whole real line. From minus infinity to infinity it is defined. And when x is greater than 0, y is obviously greater than 0. But when x is less than 0, y is less than 0. That means we have something like from the right of the y vertical, y axis, that is upward the things. That means x is greater than 0, y is always greater than 0. And for the left, if we have x is less than 0, y is less than 0. And symmetry, since the function itself is an odd function, this means that the curve is symmetrical about the origin, right? And thus it is sufficient to draw the graph above. And what are the intersection point with the axis? Y equal to x cube only intersect at x equal to 0 with the x axis, isn't it? And I mean that is why we are going to use that one. So it is symmetrical about origin as well. Now points of intersection, we got x equal to 0 equal to y equal to 0. And what about the tangents at the origin? So the y dash equal to 3x square, and henceforth at x equal to 0, the tangent equal to 0 itself, right? So the tangent at origin is the y equal to 0, that means the whole axis, x axis. So x-axis just treated as a tangent line for this curve. Monotonicity, firstly calculate y dash equal to 3x square, which is always non-negative, right? X square is a positive, so therefore 3 into x square is always non-negative, and this means that x increases, so does y. So with the x, y also increases, and the graph keeps rising. That means it will give you the monotonicity. That means with the x, y behaves. Relative maxima or extrema and minima. So dy dx equal to 0 at 0, 0, and d square y dx square equal to 6x is 0 at 0, 0. Since the second derivative is not helpful to find extrema, and let us look at the sign of dy dx on each side, right? So dy dx equal to 3x square, the sign is always greater than 0. Either it is less than, x is less than 0, or either x is greater than 0. It is always positive. Therefore, dy dx does not change the sign, right? And therefore, there are no extremum points, either it is negative or positive. Concavity. So for x is less than 0, we have a 3x square. Remember this one, d square y by d of x square is equal to 3x square. So it totally we have that x is less than 0, right? Y equal to x cube. So dy by dx equal to, right? This is not the same thing. Dy by dx equal to 6x square, and d square y by dx square is equal to 6 of x. So for x is less than 0, this will become less than 0, and for x is greater than 0, this will become greater than 0, or for x equal to 0, this will become equal to 0, right? So that means it is changing concave downward. Therefore, the curve is concave upward when x is greater than 0, and concave downward from x is less than 0, right? Because here is a concave downward and here is a concave upward, right? So asymptotes. Now can we find the asymptote? The graph has no asymptotes parallel to the any axis, y axis or z axis. Further, y beta x equal to limit x square, that does not exist. This means the curve does not have any oblique or slant asymptote as well. Singular point, I had already told you that this function is a very smooth function, and henceforth there is no singular point at all. So now we can plot this one. We had seen that with the x is greater than 0, y is going to be greater than 0. With x is less than 0, y is going to be less than 0. And it is symmetrical about origin 1. So if and there is no maxima minima, and there is no critical points here. So using those concepts we have seen that for x is less than 0, it is a concave downward, and for x is greater than 0, it is concave upward. So this is the concave upward, and this is the concave downward. Using this one, the complete graph of y equal to x cube can be sketched or plotted, right? So now you have seen that the curve tracing depends on different type of properties of the curves. There are at least 14 properties we have seen, and those properties are quite useful for us to trace those curve points. Now look at for y equal to 1 by x square. Y equal to 1 by x, we had seen that one in the, I think in the second lecture or third lecture. Now if I have y equal to 1 by x square, how I can trace that one? So looking for its simplifications, look for y equal to 1 by x square, and now look at where this function is not defined. So remember this one, if I put x equal to 0, does the function define? No. So the function itself is not defined. So function is well defined only when x is not equal to 0. Now again look at the derivative first and the second derivative of 1 by x square, and you will decide whether it is concave upward or concave downwards, and whether it has the asymptotes at that point or not. So let us do one by one. So as we have talked about its domain y, this function y equal to 1 by x square does not have any domain, except at 0, the domain is the whole real line. So, domain of this function y equal to 1 by x square is the whole real number except 0, right. And the range of the function is, since in the denominator x square and 1 by x square, that means always non-negative, not only non-negative but the positive integers. You cannot find a 0 value here, right. For that you need to x tends to infinity, but infinity is not a number, and henceforth that means you are looking for a range of that one. Range is always positive, not non-negative. It's a positive one, right. You cannot find 0. The y coordinates of any point on the curve cannot be negative. So, the curve must be above the x axis, it is always positive, we have seen here. Now, symmetric, put the value x equal to minus x, and what we get? We get the same value. So, y fx equal to minus f minus of x, the curve is symmetric about y axis, and hence we shall draw the graph of the right of the y axis first, right. So, this will give me, if I have the y axis, if I have the idea how to draw the graph of the right side of the y axis, I will plot the same identical shape to the left of the y axis, and that is how the symmetry will play a role to sketch the graph of any given function. Now, point of intersection, what do you think? If you put x equal to 0, what you will get? You will get infinity, right. The y going to be infinity, and if you put y equal to 0, what you will get? The x will also going to be infinity. That means the intersection point we are looking for does not exist at all, right. So, now we will focus on the monotonicity and concavitivity. So, for monotonicity we have to first find the first derivative. So, what will be the dy by dx? So, y equal to 1 by x square, henceforth dy by dx is equal to minus of twice by x of q, right. And similarly, d square y by d of x square is equal to 3 into 2, 6. So, this will be minus 6 divided by x to the power 4, right. So, these two numbers give me the monotonicity. So, dy by dx is less than 0 for all x is greater than 0, isn't it. So, since dy by dx equal to minus twice by of x cube, so putting x is greater than 0, the whole number is going to be less than 0, right. And what about if x is less than 0? If x is less than 0, the whole number is going to be greater than 0. So, vice versa, if x is greater than 0, the derivative dy by dx is less than 0, and when x is less than 0, dy by dx is greater than 0, right. So, since dy by dx is greater than 0 for all x is less than 0, the function is increasing in. Now, if you are having this one, so for all x is greater than 0, this function dy by dx is negative, dy dash is negative, and for all x which is less than 0, y dash is positive, right. And that means therefore, the function is increasing. So, in this range or domain, the function is increasing, and in this range the function is decreasing. That is what monotonicity gives us. Discontinuity, the graph of y is continuous in the domain of the function, that means it is continuous in domain r minus of 0, right. And relative extrema, so dy by dx is non-zero for all x in the domain, dy dx, see here, minus 2 by x cube, you cannot find the 0 here, because x is not defined, the function is not defined at x equal to 0. Therefore, there is no extremum point. Concavity and point of inflection, for concavity you need to y double dash. So, y double dash is positive, see here in the domain, therefore, the function is concave upward here, this is the positive, isn't it. This is a minus 3 into minus 2 equal to plus 6. So it's a positive. So it's always the positive. So d square y by d of x square is equal to 6 divided by x to the power 4, right? And it's always positive. It's always positive. Whether in the whole domain, that means in the whole real line except at 0. So there is no point of inflection, and the function is concave upward everywhere in the domain. Now find out the asymptote. That is the important thing. So taking limit x tends to 0 y, limit of x tends to 0 f of x, and that will give me infinity. That means x equal to 0 is a vertical asymptote. This is the asymptote here, and thus y equal to 0 is the horizontal. So y equal to 1 beta x square, we can curve like this, right? So it has the vertical and horizontal at x equal to 0 and y equal to 0 asymptote for this curve, right? As limit x tends to 0 or limit y tends to 0. Limit x tends to 0, fx is going to be infinity, and if y tends to infinity, x tends to 0. So that's what we are looking for, vertical and horizontal asymptotes. So this will be the end of this lecture, and I believe that we had explored the whole 14 properties of how to trace a curve. So trace curve or tracing the curve in a Cartesian coordinate is going to be the end here, and we are now going for the curve tracing in a polar coordinates. So thank you so much.